Hello, may I first thank the DTAS for allowing this event to take place. It is important to the Institute of Acoustics as well, I hope, as it is to Claus Elberling. My name is Barry Gibbs. I'm president of the Institute of Acoustics of the UK. It is a large institute of 3,000 memberships with a range of activities from a broad spectrum of acoustic topics, areas and activities. It is therefore both a professional institute and a learned society. And as a learned society, it is tasked to recognise excellence and give awards accordingly. And the biggest award is the Rayleigh Medal, and it's given to persons of excellent international standing for outstanding contributions to acoustics. And this year's recipient is Claus Elberling. And before I award it, I will read the citation, which will do three things. One is alert you to the fact that I'm not a clinician, that I'm not Danish, but more importantly, it will highlight the achievements which led to this award. So if you allow me. Claus Elberling graduated from the Technical University of Denmark in 1964. He graduated as an electronic engineer, majoring in acoustics and biomedicine. Since then, he has made outstanding contributions to audiology, mainly within electrophysiology, but also within hearing research, hearing aid research and development. His major research began at Gentofte University Hospital in 1968, where he developed new methods for the recording and interpretation of human electrocochleography. In 1977, he was awarded the degree of Doctor of Medical Sciences, which I believe is the highest award available in this area in Denmark. He created tools for qualifying the auditory brainstem response in otoneurological disorders and published significant work with Manuel Don from the House Ear Institute, Los Angeles. Claus has been a pioneer in auditory electrophysiology. In 1981, he was one of the first to record auditory magnetic fields from the human cortex using the acronym SQUID technique. Later, in 1985, he devised the first use of autoacoustic emission for newborn hearing screening. This led to the introduction of a Danish newborn hearing screening program. In the late 1980s, he participated in designing the first Danish CD with standardized speech material for audiological testing. It's known as Dantal, which was used in hearing clinics all over Denmark. In 1986, he began working with Oticon on a joint research project, Oden, between the three major Danish hearing aid manufacturers and the Technical University of Denmark. The investigation was into noise reduction algorithms for hearing aids. In 1990, he became head of Oticon's research center, Eriksholm. Here he made significant contributions in practically everything related to research, development and fitting of hearing aids, and was deeply involved in creating one of the first fully digital hearing aids. After 14 years at Ericsson, he stayed within Autocon but went back to electrophysiology, and until his retirement in 2014 spent 10 years researching chirp stimuli for hearing screening and assessment. Together with Manuel Don and others, he devised new design concepts for chirps, documented their behavioral thresholds, and finally investigated new methods for the acoustic calibration of chirps and other short-duration stimuli. This work has resulted in him contributing to a series of patents and about 120 publications in peer-reviewed international journals. After his retirement, Claus still spends 1 day a week at the Centre for Applied Hearing Research at the Technical University, and I'm sure he's giving more than 1 day's worth to that unit. Therefore, for his record of outstanding achievements, the Institute of Acoustics is delighted to award Claus Elberling the Rayleigh Medal for 2019. So would you come up and receive your medal?
First, I would like to thank the Institute of Acoustics and you for choosing me as the recipient of the Rayleigh Medal in Acoustics 2019. I was very surprised when I received your letter half a year ago informing me that I had been named for this prestigious award. I'm deeply honored and extremely grateful. I also want to thank you that you would come all the way from UK to present the award to me at this meeting. Many thanks indeed. Further, I am very proud that somebody thought I would be a worthy candidate for the Rayleigh Medal. This or these somebodies that have suggested my nomination are probably colleagues from within my own network and professional field. Their deed is highly appreciated. In your letter, Barry, I was asked to give a keynote lecture that summarizes the work which has received the recognition by the Institute of Acoustics. Right up front, however, I realized that the many topics I have touched upon in my research and over all the years are scattered all over our field and therefore hardly suited for a specific keynote address. So I have taken liberty to choose to focus this keynote on my developing interest into the physiology and function of the human inner ear, the cochlear, which I have researched and exploited by the mind not of a biologist, but by the mind of an engineer, and then leaving most of the other topics untouched. So, assessment of auditory function based on research and engineering. But before that, John William Struff, the third Baron Rayleigh, lived from 1842 to 1919. He won the Nobel Prize in Physics in 1904 for his discovery of the noble gas argon. But to this audience, maybe we should mention that he wrote one of the very first textbooks in acoustics. It was called The Theory of Sound and came out in 1877, followed a year after by the second volume in 78. And even more interesting for this audience he actually developed the duplex theory about directional hearing. Yeah, how many of you knew that? Actually, and he used and developed the use of the two binaural cues, intraoral phase and intraoral level differences. So that's Sir Rayleigh. Okay, leaving him right now and going on to my keynote here. I met a man during a site visit at the Central Institute for the Deaf. I met a man. I was invited there to give a speech about our new program about electrocochleography, which we have started at the Gentofte Hospital, by Hallowell Davies. And I gave that speech. Here is a recording or a figure from our first recordings published in 1971 in the ACTA journal. After the speech, Donald Eldridge came up to me and said, well, it's very nice what you talked about, but are you aware of a paper we published in the JASA 9 years ago? And here is a paper, Cochlear Response to Acoustic Transients and Interpretation of Whole Nerve Action Potentials, recorded in the guinea pig. I said, yes, I am aware of it. And then he questioned me a little more specifically, and I realized that I completely missed the important message in that paper that they have applied for the first time Highpass masking to analyze the results of the whole nerve action potential in the guinea pig. I was very sorry about that, but Donald, he said to me, don't be sorry. No, our paper was so poorly written that many people have actually missed that. But the information to you is go back and do high-pass masking on your results, on your data, electrocochleography in humans. Now, what is high-pass masking and why is it important? If you look, we take a look at cochlear excitation, you have the basilar membrane velocity as a function of location in the cochlea. And location in the cochlea is here flagged with the characteristic frequency. So you have the apex low frequencies to the left, and you have the base high frequencies to the right. And you stimulate with frequency-specific stimuli at low levels. Everything is nice and clean. The information stays, or excitation stays where it should stay. But if you take a look at what's going on at higher levels, for instance at 1 kilohertz, we see that when we go up in level, the excitation spreads up. And we call that spread up of excitation, we call it upward spread of excitation because it goes towards the base, it goes towards higher frequencies, characteristic frequencies. So even if we put in a 1 kilohertz tone, it will excite a specific area in the cochlea at low levels, but will excite a very significant area of the cochlea at high levels. So if we put in low-pass masking to the cochlea, it will go well with the cutoff frequency here at 1 kilohertz at low levels. But if we increase the level of the masker, it will mask in the end the whole cochlea. Contrary to when we do high-pass masking, it will stay put and mask the area indicated by the cutoff frequency. So if we take a click, we heard about the click today already, which is a broadband stimulus exciting most of the cochlea. Put in the click, it excites most of the cochlea. Then we put in high-pass masking. So now we record in the 2 kHz high-pass masking, we record activity coming from the lowest frequencies up to 2 kHz. We put in 1 kHz. Now we record from low frequency up to 1 kHz. And by subtracting the two recordings from each other, we will get a derived band response which actually portrays the activity in the 1 to 2 kHz band. This is called the derived band response. Eckermann called in some of his early studies the NAP, narrowband potentials. So that is the same as a derived band response. I went back home and did it. So in 1974, we published a publication in Scandinavian Audiology where you see up here the unmasked compound action potential with a little SP on the shoulder. John, there's a nice SP on the shoulder. Nice. Yeah. And down there you see the derived responses going from the base to the apex and shifting out in time following the traveling wave from the click moving up through the cochlea. So the latency of this peak is actually a reflection of the traveling wave delay through the cochlea. Now, by high-pass masking and by constructing the derived band responses, we can split up the whole nerve action potential into partials. So when we take the sum of all the partials, all the derived band responses, and add it together, or make the sum, we will arrive at the compound action potential, the unmasked. So this is a window into the cochlea. What is going on in there when we stimulate with a broadband stimulus? On top of the right, you can see the amplitude of the derived band, how it changes from higher stimulus level to a lower stimulus level. And by doing a transformation or a mapping of the characteristic frequency to physical location, for instance, Greenwood's mapping in different species, mammals, then you can take his data for humans, and then you can calculate the velocity of the traveling wave across the cochlea from the base to the apex. Here going from around 20 to 30 meters per second and down to a few meters per second. So the derived bands are a window of opportunity to look into what's going on in the cochlea, human cochlea. Eckermann did the similar thing almost at the same time, but he had the luxury of having recordings from the promontory, while ours were from the ear canal. So he got much higher responses, and he could allow himself to do a much nicer filter settings, a closer filter setting, so we got much more details out. But again, the latency function across the derived bands reflect the traveling wave delay. However, how nice it was, I met with Jos Eckermann in the mid-70s at a meeting in Paris, and we discussed this and said, well, agreed this is a hypothesis. We really don't know whether this is true, that the high-pass masking actually is acting as we think it is acting. But lo and behold, I met a man. In 1977, at the 8th Danivox Symposium, I met Professor Ted Evans at Kiel University, UK. And he was an animal electrophysiologist working as a professor in communication. And I persuaded him to invite me to go there to do the correct experiment in the cat. And the correct experiment would be that we could do high-pass masking and look at responses from the round window niche in the cat. But at the same time, we could record what's coming out on the other side from single fibers in the cat's auditory nerve. The next year, I have rebuilt my equipment, including a high-pass filter at 16 kilohertz. So I took my box with me and went to Kiel, and we set up the experiment, had a long period of days working and making it routine how we did it with an artificial animal until he was satisfied that we could do it in the right way so we wouldn't waste an animal. In the end, we did that recording, and you can see here, you see the compound action potential. To the left and to the right, you see the derived band. So exactly the experiment we did in humans, but now in the cat. It took some years, actually 4 years, until we got that publication out, which called location-specific components of the gross cochlear action potential. And the new thing here was that we could make recordings from specific nerve fibers in the 8th nerve. Here we have the PST, post-stimulus time histograms, in response to the click without and with masking from 3 different units, 10 kilohertz, about 5 kilohertz, and about 2.5 kilohertz here. And no masking, 16 kilohertz, 8 kilohertz, and 4 kilohertz. And I've indicated with the arrow there, there's no light in this one here, but the arrow here, it is indicating where the characteristic frequency of the fiber is located, here and here. You can see everything is untouched until the filter goes over the characteristic frequency. So 10 kilohertz, and we have 16 and 8 kilohertz. So now it masks completely. Now it masks completely 8 to 4, and here 4 to 2, and 2.5 kilohertz was the sign. In conclusion, we were able to confirm that based on these recordings that the high-pass masking is doing what it's supposed to do. Then I met another man. There's been a lot of men and quite a few women as well in my life. I met a man in 1979 at the ERA meeting in Santa Barbara. And that is, of course, Manuel Don at the Hotel Institute, became a very close friend and still is, and we have been working together for many years. I persuaded him to invite me to the Hotel Institute as a guest researcher, and I went there in 1982. I spent a half a year there, and we worked on quality estimates of ABR, threshold characteristics of the ABR, residual background noise in the ABR recordings, and over the years we have published 14 publications, made 14 publications together. Now we have to make a little jump in time, because what I'm really going to follow up on is going on quite later. But in between I did recordings of the magnetic fields from the auditory cortex and made 6 publications together with people from the physical department at DTU. We did 7 publications on transient otoacoustic emissions in newborns quite early. And I did make together with Carl Ludvigsen and Paul Erik Lyregard, the Danish speech material on CD. And then I had an intermission of 18 years where I didn't do much electrophysiology, but was focused on doing hearing aid research. Back to Manidon. Now we move into the brainstem response. And Manny, together with Jos Eckermont, had done a lot of important recordings and publications on that issue. Here you see the click ABR on top in red, and you have the derived band from the ABR following below, going from the base to the apex. And the latency is again a reflection of the traveling wave delay, but shifted by about 4 milliseconds. Because as you see here, the N1, or the wave 1, to wave 5, is delayed by about 4 milliseconds. So if you take the latencies over here and subtract about 4 milliseconds from them, you will get back to the level of the cochlea of the wave 1. Here, Manny and Jos Eckermont, in a very important publication in 1980 from JASA, they show how the derived band amplitude change with characteristic frequency or location in the cochlea. And up here you can see at higher levels, actually down to 30 dB, most of the cochlea is active and contribute actively to the wave 5. Manny and Jos Eckermont, they were interested in improving diagnostics for cerebellopontine angle tumors. Therefore, he looked at this delay, the traveling delay in the cochlea, as some hindrance in obtaining a large response. So he developed what we later call the output compensation. We took the output, here the derived band, and lined them up so they were on top of each other, as though the cochlear delay was not there. All fibers in the cochlea are excited at the same time. And then he added them up and created what he called the stacked ABR. They are stacked on top of each other. I wanted something quite different. I wanted to improve the efficiency of recording ABR or ASSR in newborns. So if you look at the input to the cochlea, here a click, now consisting in this example of 4 octave band stimuli. So if you take these 4 octave bands and add them together, you will get that click here. It's a frequency limited click going from 350 to 5.7 kilohertz. Now, and due to the traveling delay, it will take some time for that stimulus, part of the stimulus, to work its way from the base of the cochlea all the way up, and therefore the ABR to that stimulus is coming later. So this is actually the sort of a derived band ABR to that one. Now, if we start shifting the stimuli back, so the 500 Hertz is shifted more back than the 1000, 2, and 4, but if you shift them back in the appropriate way, then the responses are on top of each other, and then we add the stimuli together. We don't have a click anymore, we have a chirp. The chirp is a stimulus where the low frequencies come before the high frequencies. You need to see my little man. I've shown him before to you. I have the little man. He put a hook into the low frequencies of the click. And then he draws it out. Now he is pleased. He stays there. I didn't do it just for fun. But to give you the important information, we have done nothing to the click other than changing the location of the stimulus, the frequency components, which means that the click and the chirp has the same spectrum, power spectrum or amplitude spectrum, and therefore they have the same behavioral threshold, which has been proven by several investigators. In order to make a click or a chirp, we need to have a cochlear model, a model of the traveling wave delay. And Manny and I, we pulled out his old data from 2 publications, all in all from 81 normal hearing subjects. And here you see the latencies of the derived band responses over here, minus about 4 milliseconds in order to pull it back to the level of cochlear. And over here you see the mean and the 2 extreme curvatures. The data were fitted to a power function with 2 constants. The delay is equal to k times frequency in the power or minus d, and k and d are constants. We applied, together with some people in Germany, Mario Cebulla and Eckhard Stürzebecker, that chirp together with click in 49 normal hearing subjects using an ASSR paradigm. That means that the stimuli were delivered at a rate of 90 per second. And here you see that the chirp are generated much higher responses than the click, both at 50 and at 30 dB, both low levels. Normally you don't see the temporal waveform when you do an ASSR because you work detection-wise in the frequency domain. But we did some tricks and reported everything for that study in the temporal domain. From the data, you saw the massive spread of data and the 2 different curvatures in the extreme. And some other data indicated there might be longer latencies at lower levels. So we did an experiment where we changed chirps. We had one chirp 1 to chirp 5, around chirp 3, which was the average chirp data that we showed you before. So we used these 5 models, new models, and created 5 chirps, presented that together with the click. And the Don chirp, based on Don's data, was later named, not by me, as the ce-chirp, and it has stayed put there. It's called the ce-chirp now. Now, if you look at the ABR amplitude from 20 normal hearing ears, at those three levels here, 20, 40, and 60 dB, you would see that there's a remarkable change in the data configuration. The non-chirp here is sort of optimal, giving the highest ABR amplitude at 40 dB, but a shorter chirp is probably better at 60 dB, and at 20 dB, we didn't even get the maximum. I'm the first to say that I made a mistake here, and I kicked myself ever since for that, not including 80 dB. I was so preoccupied, so focused on what's going on at low levels, because we were into newborn hearing screening, that concept, that I didn't see that. And now you can see that we should have included it, but we didn't. Here are the data in the grand average data, and what is important to see here, everything looks actually fine except there. Actually, the ABR is completely distorted here. What's going on? Upward spread of excitation. Here we have the chirp. It contains different frequency components at low levels. If we go up to high level, for instance, the 1 kilohertz frequency component, then it will excite the base of the cochlear, but it comes in with another latency because we have made the correction for it. And then everything breaks down. Okay. The temporal model we used is not sufficient. It's insufficient. It's not enough. We have to add more. We have to do something else. So then Manny and I, we approached it in a different way. We say, well, at that time we had developed octave bands from the chirp. 4 octave bands, and here they are. So you can see that the 4 octave bands down here, if you add them together, it will give them the chirp up on top, except that we missed the 8 kilohertz. That was not included. These octave band chirps were out in the beta testing, and we were able to collect the data from that beta testing from about 48 normal hearing subjects. And with that timing you saw before with the octave bands, we would expect that they all, for all levels, would give the same latencies on top of each other because we compensated for the temporal delay in the cochlea. But lo and behold, it didn't. Yes, it did around 40 dB. It was okay. But here, the chirp should be shorter. This is exactly what we found in the other study. And up there, the chirp should be longer, also what we found in the other study. But here we had a really good grip on what was going on, and we were able to formulate how the latency function should change with level of the broadband chirp. So here you have 20 dB NHL, 80 dB NHL, and the ce-chirp is right in the middle, around 45 dB. So we have, and we coined the term LS chirp, the level specific chirp. And here they are. But remember, the short chirp here is not because the travel delay in the cochlea is lower or faster, that it moves faster through the cochlea. It's because that we have to make a compromise between obtaining full temporal compensation and at the same time avoiding the negative effect of upward spread of excitation. So it's a compromise. And what did we get out of it? Here we have the grand average recordings, again from 20 years. And you can see the LS chirp here and the ce-chirp here. Hey, look at that. Here you see again distortion. It's not a well-defined ABR. It's distorted due to upward spread of excitation. If we make the chirp shorter, it gives a beautiful and high response, and we are back up here in the amplitude input-output function. Now, you cannot go out in the clinic and use a chirp for newborn hearing screening or for assessment of hearing without having a proper calibration. So we set out to do that. That was our duty to perform that. And we made a study where we found the reference equivalent sound pressure level, which is a peak-to-peak equivalent sound pressure level. This is the measure which is standardized for brief stimuli. You compare the peak-to-peak value with the peak-to-peak value of a pure tone, and then you say the pure tone sound pressure level is equal to the peak-to-peak equivalent of the short stimulus. And we were not alone. PTB, Physikalisch-Technische Bundesanstalt in Braunschweig, they had done the same for us a year earlier and came up with data that matches, or we came up with data that matched their data very closely. For years, it had troubled me that we have this irritating peak-to-peak value to run around with. And every time we had to do something, we had to take an oscilloscope and measure there. It's inaccurate and bothersome. Go out for calibration somewhere, you need to have an oscilloscope with you. So we set out to try to change that and defined the use of the RMS value instead. So we can measure that in a sound level meter directly. So we developed the concept and the mathematics behind. So today we can now transform peak-to-peak value to RMS value. And to show you how much more available or the RMS value is, if you look at the full curve here, that is the pure tone reference thresholds you use for normal audiometer calibration using the insert earphone ER3A in the occluded ear simulator. If you take the data that we measured and converted, RMS value for octave band chirps and for 212 tone bursts, which are used regularly for ABR and electrocochleographic measures, and specify the rate of 20 per second, then you can see the values are here. The two sets of frequency-specific data are on top of each other and deviate only a little from the pure tones. The behavioral threshold of brief stimuli relates relatively closely to the time average sound energy presented at the tympanic membrane. What can the chirp be used for? Hearing screening in newborns. Broadband chirp at 35 dB NHL, applying ASSR recordings. They're very fast, and quite some clinics and a lot of data are available to show that it is a very nice way to do newborn hearing screening. You can use it for hearing evaluation, both in children and adults, octave band chirps, either ABR or ASSR. And using the ASSR system or technique, you can obtain thresholds at 4 frequencies in both ears within 30 minutes. Quite a few publications are out and have demonstrated that this is a fact. What about validation of hearing aid fitting in infants? This is the last thing that I have touched. And using octave band chirps and ASSR recordings, I will just show you the idea behind that. You take the octave band chirps here and set them up as you would do for an ASSR recording. That means it is fast, a fast rate, not about 90 per second, but not 90 for all of them. They are coming out with different rates, so we can pick them up in the spectrum. Then we shape, some of them we shape to have the same long-term spectrum as speech, and then we modulate the stimuli with a simulated speech envelope, and then you put it out through a speaker. And the sound of that will be very close to the sound that James presented to you before, because the modulation will drive a perception of that it is speech. So this stimulus will be able to evoke an ASSR, and it will also be able to pass through a hearing aid as were it a speech signal. So the hearing aid will stay in speech mode, even if it is such an artificial signal that comes through. We have recently made a publication about that here. Now, all this I have not done alone. Of course, nobody can do that alone. I have had inspirators, colleagues, and co-workers, starting with the man who actually introduced me to auditory electrophysiology when I came to the Gentofte University Hospital. Highpass masking, we had talked about. Quality estimation with manual done, we had talked about. We didn't talk in details about magnetic field recordings, transient evoked emission for screening of newborns. And we didn't talk about another big part, hearing aid research, with a lot of beautiful colleagues, Paul Erik Lyregård, Carl Lovisen, Stuart Gatehouse, Gitte Kaiser, Torben Poulsen, Thomas Lunner, Klaus Nielsen, Kim Valby Hansen, Graham Naylor, and the Eriksholm team in that period where I was there. ASSR detection and new stimuli together with Egerhard Stürzebecker and Sebulla in Germany, chirps with Manuel Don, Sinnett, Søren Madsen, Bo Christensen, and Johannes Kallø. Some of them are here today. Calibration of chirps and clicks, Thomas Fetk and Johannes Hensel from PTB in Braunschweig, and Lau Krone and Torben Poulsen, Christian Götzke. And then fitting of hearing aids together with James and Søren, and students from IRU and DTU. Thank you that you were listening to me. Thank you.